Hi, in this video, I'm going to continue on the topic patterns in the chemical world, and in this video, I will be focusing on the transition metals. So let's get started. Now, what do you mean by transition metals? Let's underline the definition. Transition metals are defined as metals that can exhibit two or more oxidation states in compounds. Now, pay attention. A lot of you guys will miss out the last one. Compounds. So an example would be Fe. Right? Fe is an example of transition metal because Fe can form FeCl2, also it can form FeCl3, isn't it? So if you look at these two compounds, the first one, Fe is having an oxidation number of +2. Here it has a +3 oxidation state. So this one fulfills the criteria. Okay, it has two or more oxidation states in compounds. Now, some metals, for example, I use magnesium. All right, magnesium. Now, magnesium can only form one compound, maybe MgO, right, with one oxidation state +2. It doesn't have +1, it doesn't have +3, it doesn't have +4, something like that. So this one, Mg does not fulfill this criteria, so Mg cannot be classified as transition metals. Okay? Now, why is it important that you have to include the word compound at the end of the definition? It's because if you simply say that, if they can exhibit two or more oxidation states, then you realize that actually Mg is having an oxidation state of 0, right? Also Fe. So if you do not have the word compound, then basically all the metals could be transition metal because two oxidation states, isn't it? So bear in mind to have compound at the end of the definition. Okay? Now, but what are actually the transition metals? Where can we find them? Now, on the periodic table, the transition metals are a group of metal sandwiched between group 2 and group 3. So group 2 is here, group 3 is here. So over here, there's a bunch of metals with no group number. Those are called transition metal. Okay? So if you look at period 4, it starts with scandium, and then titanium, vanadium, chromium, manganese, iron, cobalt, nickel, copper. Now notice that zinc is not considered as a transition metal. The reason is because zinc is similar to Mg. Zinc can only have one oxidation number in compound, which is +2. Okay? Zinc can only have +2 in compound. Right? It does not have +3, +4, something like that. Okay? Now, here there are some special features about transition metals. So down here, they all have special electronic arrangement. Now, if you look at the right-hand side here, I have listed a couple of transition metals. The transition metal is only these. These are the transition metals. But just to show you that, now, calcium, is 2882, right? The next member, scandium, you may think that it will be 2883. However, bear in mind that the third electron shell can hold at most 18 electrons. So the magical thing is, in fact, after we put 2 electrons into the fourth shell, extra electron will be added back to the third shell until it is full. So you see, here is 2892, and then 2810-2, 2811-2, something like that, until it becomes 2818-2, which is zinc. And after that, extra electron will be added back to the fourth shell because the third shell has already been full. Okay? So this is the special electronic arrangement. You don't have to know why. This is just like this. So you realize that in the outermost shell, they all have 2 or 1 outermost shell. Remember that the outermost shell actually determines the chemical properties. of an element. So we say that these transition metals, they have very similar electronic arrangement. So they have similar properties. Okay? So over here, you see, transition metals have either 1 or 2 outermost shell electron. Okay? Across a period, additional electrons are added in the next inner shell rather than the outermost shell. So if we are talking about period 4, then the extra electron is added onto the third shell. If we are talking about period 5 elements, then the extra electron will be added to the fourth electron shell. Okay? Therefore, they have similar, now not the same, similar chemical properties within the period. Okay? Now, the second thing is, down here, they have high melting points. Now, mainly high melting point are the boiling point, we are talking about solid metals, so we don't really talk about the boiling point. Now, transition metals, they have giant metallic structure, right? They are all metals after all. And we say that for giant metallic structure, the melting point is generally high, and the melting point depends on the number of delocalized electrons, right? So, for these bunch of metals, you may think, hey, sir, they are either having 1 or 2 outermost shell electron, then should not be having very high melting point. However, the magical part for transition metal is that the electrons from the outermost shell as well as the next inner shell, in this case the third shell, can both be contributed to the sea of delocalized electrons. Therefore, they have more than just 2 outermost shell electrons contributing to the delocalized electron. They could have more. Therefore, the strength of metallic bond is exceptionally strong when compared to group 1, group 2, group 3 metals. Okay? If you check out the data booklet, usually the transition metal, the melting point is over 1,500 degrees Celsius. And when you look back to the group 2, group 3 metals, we are talking about 1,000 or few hundred melting point. So they are exhibiting exceptionally high melting point. Remember, there is a metal that is used in light bulb, which is called tungsten. Now, tungsten is also a transition metal, and the melting point will go up to almost 4,000 degrees Celsius. Okay, so you can tell transition metal do have a very high melting point. Okay, now next page, page 13. This one, very important. I would say the entire topic, the most important thing is the transition metal, especially their properties. So here you must be very, very familiar with. Now there are 3 general properties for transition metal you need to bear in mind. First of all, they form colored ions in aqueous solution. Okay, in aqueous state. Okay, and secondly, they have variable oxidation states. Basically, just like what I introduced the definition of transition metal, they could have different oxidation states in compounds. Okay, and lastly, the catalytic property. A lot of the transition metal or the transition metal compound can be used as catalysts in a lot of different processes. Now, the first one here, colored ion, you just have to memorize these colors. Okay, a lot of them we have already covered in the previous topic. So perhaps you need to recognize that for chromium, the chromium 6 ion is yellow in color. Over here, manganese 3 ion is red in color. Okay, titanium 3 is purple. Okay, now here you need to memorize some example, and I will expect you to memorize something that you are more familiar with, such as iron, chromium, manganese, because in the DSE exam, there may be some essay type question asking you to illustrate some properties of transition metal, and if you want to mention about colored ion, it will be best to substantiate with some real example. Okay? Now, the next property is variable oxidation state. Now here, this table basically showing you all the possible oxidation states of the transition metal. Now, the one that I have underlined is the most stable oxidation state. So you will often find these transition metal, if they are in a compound, then they will usually having these oxidation states because they are the most stable one. Okay. Now, you notice that a lot of these will have at least 2 oxidation states in compounds, right? Now, scandium is a special case. It is considered as a transition metal, but it only has 1 oxidation state in the compound. Now, the reason here, you don't have to know why, but scandium generally considered as a member of transition metal. Actually, the definition of transition metal varies for different syllabus or different level. If you're interested, you can ask me later. But anyway, scandium is counted as a member of transition metal, but zinc is not. Zinc is not. Bear in mind. Now, so for these transition metal, it will be best if you can remember some of the possible oxidation states. Now, you may realize that actually most of them can exhibit +2 and +3 oxidation states, except copper. Copper cannot. So I think you can at least memorize +2, +3. Okay? Now, down here, this is some example showing you that, for example, iron, it can exist as iron 2 and iron 3 in a compound. So iron 2 ion is a very common reducing agent. You learn it in the topic of redox process. And iron 3 is an oxidizing agent, despite this is not a very common or very strong oxidizing agent, but it can act as an oxidizing agent. Okay? Now, manganese. I think you need to spend a little bit more attention to manganese. Manganese can have 3 oxidation states in common compounds, and they have different color, they have different application. Now, first of all, Mn2+ in solution, if you remember, is having a very pale pink color or even colorless. Now, MnO2, do you remember that we have talked about this when we talk about redox, when we talk about zinc carbon cell? Inside zinc carbon cell, we have a lot of graphite mixed in with MnO2. And MnO2 is act as an oxidizing agent to oxidize any hydrogen gas formed into water. This is to prevent any gas bubble trap on the graphite cathode, do you remember? So MnO2 is not the first time we see it. Okay? Now MnO2 is a black solid. It is used as an oxidizing agent, not only in zinc carbon cell but also in laboratory preparation of chlorine gas. It is done by adding MnO2 into corn hydrochloric acid. Basically, this oxidizing agent is oxidizing the chloride ion in HCl into chlorine gas. Okay? MnO2 is also a catalyst to speed up the decomposition of hydrogen peroxide. So you can also put a remark here. Okay, as a catalyst, okay, can speed up the decomposition of hydrogen peroxide. Okay? Now down here, MnO4-. So it is a purple solution. You learn about that. It is a very powerful oxidizing agent. So in acidic or neutral environment or condition, MnO4- is usually reduced to Mn2+ by a reducing agent. Okay? And this is the ionic half equation for the reduction of MnO4-. And in alkaline solution, MnO4- will reduce into MnO2. Okay? So the ionic half equation is a little bit different, and pay attention that since it is an alkaline solution, we have OH- instead of H+. Okay? So like I said, if the question asks you to point out some general features of transition metal, it will be best if you substantiate with some real examples. Just like here, if you want to mention about transition metal can exhibit variable oxidation state, these are 2 good choices, good examples for you to illustrate. Okay? Not only talking about the formula of the compound, with different oxidation states, but it also shows you the colored ions, right? They have different color. Fe2 plus, pale green. Fe3 plus, yellow or brown. Here, Mn2 plus, very pale pink. MnO2, black. MnO4 minus is purple. See? So these are good choices of examples to substantiate your answer. Okay, so we have a practice question here. Spend some time to work on this. Okay, let's have a look. Now, explain why manganese 4 oxide can be used as either an oxidizing agent or reducing agent. Okay, so first of all, manganese 4 oxide, we say that the oxidation state of Mn in MnO2 is plus 4. Okay, and we say that the oxidation state of Mn can change from positive 4 to positive 7, as in MnO4 minus. Okay, therefore it can act as a reducing agent. On the other hand, we see that the oxidation state of Mn can change from positive 4 to, now this one you can choose positive 2 or even positive 3 because those are possible oxidation states. Positive 2 as in Mn2 plus. Okay, therefore it can act as oxidizing agent. Okay, so basically telling people that the oxidation state of Mn in MnO2 is able to change, is able to increase and decrease. So it can act as both oxidizing agent and reducing agent. Okay. Now, question 2. Based on common features of transition metal, state 2 reason why zinc is not considered as transition metal. Now, so based on the common features, we only talk about 2. So the first one is colored ion. So the first one we will say it doesn't form. Colored ion, okay, in aqueous state. And secondly, it contains one oxidation state in compound only. Okay? So that means it does not have the variable oxidation state. Okay? Now 3. Titanium ion or compound can have oxidation state of +2, +3, and +4. Which of the following statements are true? The first one, iron 3 ion is purple in color. This one is correct. Now, if you don't know this one, you can also look into the other choices. Here, titanium 2 sulfide can be a reducing agent. So reducing agent means it undergoes oxidation. So +2 can definitely become +3, +4. So this one is okay. Now, titanium 4 fluoride can be act as a reducing agent. This time, it is not correct. Because again, if you want to be a reducing agent, you need to undergo oxidation. But you already reach your maximum oxidation state. This one is already +4. So that's why you cannot further oxidize. So the answer would be A. Okay? Next one. Next one is talking about the catalytic property. Okay, again, this one we have repeated many times because catalyst appears in several different topics in chemistry. Now, a catalyst is a substance that can alter, that means change, the reaction rate without undergoing permanent chemical change. right? Now, catalyst, it can participate in a reaction. That means it can be consumed at the first place, but at the end, it will be regenerated. Okay? Some catalysts will do it this way. Some catalysts will simply do not undergo any chemical change. Okay? But for details, it is out of the syllabus. Now, transition metal ions, you may ask, how are they able to catalyze a reaction? Especially, how do they catalyze by participate in the reaction? Now here, we say that transition metal ions or metals, they can participate in redox reaction to form intermediate compound. What do you mean by intermediate? Now, intermediate is not the product, not the reactant. Intermediate is in between reactant and product. Usually, when a reaction takes place, it takes several steps, right? Not all the reaction go one step. It could take several steps. For example, A can become B, and then B becomes C, and finally C becomes D. So the reaction may not simply A one step changing to D. It may take several steps. So when A becomes B, B is considered as an intermediate. And B becomes C, C is also an intermediate. And at the end, C becomes D, D is the product. Okay, so that's the idea. Now, we say that transition metal ions and compounds, they can participate in the reaction, basically forming intermediates. And why do they able to form intermediates? Is because they are having variable oxidation state. So they can change their oxidation state in order to speed up a reaction. How does it work? Let's have a look at these two examples. Now, the first one, we have a reaction between iodine and peroxide disulfide ion, S2O8 2-. Okay? Now the reaction happens very slowly by itself. This is because you notice that I- and S2O8 2-, both of them are negatively charged. And for a reaction to take place, it takes the species to collide on one another, right? Having both chemical species carrying the same charge, it is very difficult for them to approach each other and get collision. Therefore, this reaction is very, very slow. So you see here, very slow because collision of the two reactants of the same charge. Okay? So how can we speed up the reaction? We can add iron 2 ion or iron 3 ion to catalyze the reaction. When you add iron 2 ion, then the iron 2 ion will first react with S2O8 2-, forming Fe3+ and SO4 2-. Now, during this process, you may realize that the oxidation state of Fe changes. Of course, from +2 to +3. Okay? So Fe2+ is oxidized. That means Fe2+ has lost an electron. When they lost an electron, the electron is given to the S2OH 2-, forming SO4 2-. Okay? So S2OH 2- is reduced. Okay? Now, in the second step here, Fe3+, which is generated in the first step, will then reacts with I- to form back Fe2+ and I-. Okay? Now you notice that in this reaction, Fe3+ is reduced back to Fe2+. So we say that Fe2+ is regenerated. Okay? Now, also, when Fe3+ is reacted to form Fe2+, it is reduced. That means it has gained an electron from I-. Okay? Now here, I- should have a 2 here. Okay? Now, during this process, it has accepted an electron from I-. Okay? So, overall speaking, what it does is, here in the first step, Fe2+ donate an electron to S2O8 2-. And after that, Fe3+ will collect the electron back from I-. So this guy, Fe2+, is acting like an electron carrier. So instead of I- directly transfer an electron to S2O8 2-, Fe2+ does the job for I-. Fe2+ will donate an electron to S2O8 2- instead of I-, and after that, Fe3+ will collect the electron from I-. Okay? Now, even though it has separated into 2 steps. However, the rate should be much faster because you see that we are involving collision of oppositely charged ions. So it is much more easier to collide on each other than collision involving species of the same charge. Okay? So that's why the 2-step reaction pathway is much faster because both steps involving collision of the 2 species of opposite charge. Okay? So that's why we say that on the top here, I haven't underlined it, we say that the transition metal compounds, they act as electron carrier. Carrier is basically the one who carry the goods from A to B, okay, traveling around, and they're good at transferring electrons, basically. Okay? Now, another case study, this one has been asked in DSC. It's a very interesting example. Now here, there's a reaction between oxalate ion and permanganate ion. Now, oxalate ion is very similar to ethanoic ion. It's basically having like 2 ethanoic ions together. There's no negative charge over here. Okay? So, the reaction between these 2 ions, again, you can predict the reaction should be very, very slow. Not only because we are having 2 negatively charged species colliding with each other, but when you look at the equation, you see 5 oxalate colliding with 2 permanganate and also involving 16 H+. So altogether, how many? Like 23 particles colliding at the same time at the right orientation with sufficient amount of energy. What are the chances? Very, very low. So you will expect this reaction to be very, very slow. Okay? Now, here, we say that the reaction is very slow because it's involving collision of 2 reactants of the same charge, similar as before. However, the reaction can be accelerated by itself. So the reaction can accelerate itself. Very interesting. And if you look at the right-hand side, I have a graph showing you the change in concentration of permanganate, which is one of the reactant, against time. You notice that at the beginning, the slope is not very steep, very slow reaction. But gradually, the reaction increases. The slope is getting steeper, and during the middle of the course of the reaction is actually fastest. This is quite contradicting to what we have learned in the topic rate of reaction, where the reaction should be the fastest at the first place, where the concentration is the highest. But this one is a special case. The reaction is the fastest during the middle of the reaction. And why is it like this? Well, the thing is, because the reaction produces Mn2+. Okay, if you go back to the equation here, the reaction produces Mn2+. And Mn2+ is able to act as a catalyst to speed up the reaction. So, what it does is, if you go back to this reaction, if you look at the oxidation state, MnO4, the Mn is having +7, and C2O4, the C over here is having the oxidation state of +3, isn't it? Okay? And you can tell when the reaction proceeds, it produces carbon dioxide, this one is +4, and this one is +2. So basically, oxalate ion is oxidized, permanganate ion is reduced. Okay? So basically, C2O4 2- will lose an electron to permanganate. Right? We lose electron to permanganate. But like I said, a direct transfer of electron by collision is very difficult to achieve. So that's why it requires some help, perhaps from Mn2+. So down here, you see, the Mn2+ is able to first react with MnO4-. Basically, Mn2+ will react with MnO4-, forming Mn3+. Mn3+. Okay? Now, during this step, the MnO4- will receive electron from Mn2+. Okay? So, Mn2+ will provide electron to MnO4- instead of oxalate ion. And after that, the Mn3+ will go to find the C2O4 2-, and the Mn3+ will collect electron from oxalate ion, and therefore forming carbon dioxide and Mn2+. And you see Mn2+ is regenerated. Okay? So that's why Mn2+ is acting as a catalyst. Okay? So you see, Mn2+ produced that reacts with MnO4- forming intermediate Mn3+, and the intermediate Mn3+ is then converted back to Mn2+. Okay? So Mn2+ is acting as an electron carrier, facilitating the electron transfer between oxalate ion and permanganate ion. Right? And this special example has a name. We call this one autocatalysis. Autocatalysis. Auto means do it by itself. Catalysis basically means catalyst. Okay, so the reaction will catalyze itself, meaning that the reaction will produce a product which can act as a catalyst of the reaction itself. Okay, so this is an interesting example which has been asked in DSE. Alright, so do pay attention to that. Now lastly here, we have a practice question. You can pause the video, spend some time to work on it. Alright, let's quickly have a look. So 3 general properties. So the first one forms colored ions in aqueous state. Secondly, exhibit variable oxidation states. And thirdly, catalytic property. Okay? Now, question 2. Iodide ion reacts with peroxo disulfide ion to yield elemental iodine and sulfate. Write a balanced ionic equation. So we have I- reacts with S2O8 forming iodine and sulfate. So 2, 2. Okay? Explain briefly why the reaction is very slow. Well, because it involves collision of 2 chemical species of the same charge. Okay? Now, explain how copper 2+ can speed up the reaction. How copper 2+ can speed up the reaction. So, now copper 2+, first of all, you need to know copper 2+ is able to form copper plus or even copper, right? So, copper 2+ can act as an oxidizing agent and itself undergo reduction. Okay, so it is able to accept an electron from these chemical species. So perhaps the Cu2+ will first react with I-. Okay, so Cu2+ reacts with I-, accepting electron from I-, forming Cu+ and I2. Okay, you can balance the equation by adding the 2 here, the 2 here, and the 2 here. So it forms a Cu+ intermediate. The Cu+ will then react with the peroxo disulfide ion, forming back the Cu2+. Remember, the catalyst must be generated at the end, and then the sulfate ion. Okay, so there are 2 of them, and then I think we have to have 2 of them, 2 of them. Okay, then you see these 2 reactions. Then you can say these 2 reactions involve collision of species of opposite charges, which are much faster. Okay? So that's the idea. Okay? So the last page here is nothing but give you some idea about the importance of transition metal involving in the industry or other application. So very often transition metal can be used as a catalyst, and also because of their higher melting point and also their strength, they are exceptionally hard and strong as well. They can be used as components in certain materials. Also, they have some medicinal application and maintaining health. Now these are the period 4 transition metal to simply give you some idea about the application and importance. Titanium, you did learn about that. It's a very good material, light, strong, and resistant to corrosion. So it can be used as making the body of space shuttles. Okay. Chromium, very beautiful appearances, can be used for electroplating. Manganese for dry cell, and this is also what I have mentioned as a catalyst to catalyze the decomposition of hydrogen peroxide, especially when you wear contact lens. Those monthly contact lens where every day you have to clean it after use, that cleaning bottle inside will contain a piece of manganese for oxide. Okay, so that really has daily life application involving in the cleaning of contact lens. Iron, of course, used to make steel. Steel is used to make infrastructures. Iron is also used as a catalyst in the Haber process. Okay. It is also a structural component in hemoglobin in red blood cell. If you do biology, you will know that. Cobalt can be used in radiotherapy. This particular isotope is used to kill cancer cells. Nickel can catalyze the hydrogenation of alkene to form margarine. Okay. Copper, as a water pipe or power or electrical cables because it is exceptionally ductile and it has an exceptionally high electrical conductivity. Zinc is not a transition metal, but anyway, I just put it here. Got platinum, rhodium. These guys are also transition metal, and they can be used as a catalyst in the catalytic converter. Yeah, so these are some examples. Perhaps you can have a look, and it will be best if you can recognize some of these. So that's it for this video, and this is also the end of this topic, patterns in the chemical world.